Amides, a lot of it's similar, right? The only difference is instead of having two oxygens attached to a carbon, you have an oxygen and a nitrogen attached to said carbon. But I still have a carbonyl carbon that I should be looking at here. I should still understand that that originally came from a carboxylic acid. This derivative came from a carboxylic acid. So I should know what part of this molecule was from my original carboxylic acid. It's this part over here. Again, I'm not circling an oxygen because there's no oxygen there, right? The other extra oxygen in an ester that I have right here, right? It's not there this time because that's a nitrogen instead. And that nitrogen was definitely not part of my carboxylic acid. That's the only reason I'm not circling that. But otherwise, since this has 1, 2, 3, 4 carbons, that obviously came from a butanoic acid. But the way that I name this thing is a little bit different. I don't use my carboxylate name because, again, I don't have that oxygen that we were talking about before. So I can't actually have a look like that, right? A carboxylate has an oxygen here that is not here currently, so I can't use that kind of name. But I can still drop the ending, the oic acid, and add a new ending, which should be easy to remember because it's the name of the molecule, right? So this thing becomes a butanamide. So in order to name that amide, right, you just drop the ending, right? You had that 4-carbon chain, it's a butanamide now. Otherwise, there are variations of these amides, right? Right below here, I added a branch, a carbon off of the nitrogen, right? And then you just have to understand, well, it's still a butanamide, but now I have a methyl group attached to that butanamide. And that methyl group is attached to a nitrogen. So just like before with amines, I need to put an N in front because that's telling me where the methyl is attached. Because otherwise the methyl could be attached anywhere on the carbon chain over here. It could have been right here. It's not, but N-methyl butanamide is the name for this molecule. Because it looks similar to the one above. The only difference is it's got a nitrogen, or excuse me, a methyl group attached to that nitrogen. So that's how you name it. Breaking down amides is similar to the ester reactions. If I wanted to break this down, which again I would need water to do, I'm going to, again, break this bond right here. The only difference is this time when I draw this out with those two pieces that are separated from each other now, I'm going to bring in parts of the water, but this time I'm going to add the hydroxyl group to the carboxylic acid side of this because there wasn't an oxygen there like we were discussing before. The other hydrogen ends up attached here, which means this molecule is actually an ammonia, right? NH3. I can draw it out the other way so I can kind of see that hydrogen that came from the water, but it's really just an NH3 if you're going to draw it, write its formula normally. But those are my two products. That's all I got to do in this case. Whereas if I broke down this one down here, the difference would be, okay, I still have those two pieces. Now I have a methyl group hanging off of that nitrogen, but I still have those same two pieces. And then this time, again, even if I didn't show you that there was a water, there's still a water. I have a hydroxyl group here, I have a hydrogen here. But this is where your amine understanding from before comes into play, right? Know that there was a hydrogen on this nitrogen already, so now there's going to be two hydrogens on this nitrogen, and I can draw them out this way. Or I could do more of a, okay, H2 and with a branch off of it. I can write it like that, one way or the other. You don't have to do both things. Just like up here, I could have had that answer one way or the other. You could do NH3 or you could draw it out like this. I don't really care. But understand that it is important to have the right number of hydrogens on your nitrogen at all times. That is something I actually graded you on before. I'm going to do it again. So nitrogens always make 3 bonds. So you should always have 3 things attached to that nitrogen. Whether there's 2 hydrogens and a carbon, or 2 carbons and a hydrogen, or 1 carbon and 2 hydrogens. There's always 3 things attached to that nitrogen. So make sure you show that. Otherwise, like I said, pretty simple, similar to before. I threw in this example because, again, you can have 3 things attached to a nitrogen. This time there are 3 carbons attached to the nitrogen, which makes this nitrogen kind of tertiary, right? And if I go back here, this amine is primary, right? This amine is somewhat secondary, right? This one's kind of primary because it's only got the 1 carbon on it. This has no carbons on it. So this is not an amine at all, right? It's just an ammonia. So that's kind of a 0 degree version of a nitrogen that has 3 hydrogens on it. But it's important to still be able to recognize those things that we talked about before. Again, I got to name this, so I'd have to figure out, okay, what's what? This carbonyl carbon and everything else was part of my original carboxylic acid, so I have to name that appropriately. That would have been called a benzoic acid. Oops, forgot to see. Before, I am going to change that name to call it, to give this amide a name, but it's a little bit different, although it's actually kind of the same. See how we dropped the oic acid and add amide? I'm going to do the same thing here. Sorry, I hit the wrong direction. I'm going to drop the oic acid and add amide to the end. This will be called a benzamide, or at least that's the base for my name. Whereas I still have a couple carbons attached to that nitrogen, and I have to name those parts appropriately. Now remember, these 2 things are different, so I can't use like a di or just name it once, obviously. I got an ethyl and I got a methyl, and I got to use alphabetical order, and I have to show where those things are attached. Both things are attached to the nitrogen. So I have an N-ethyl and methyl benzamide. So again, should be able to see all parts of that. Got a methyl, I got an ethyl, and then my benzamide is this ring, and everything else that came from my carboxylic acid. I can break this down. Again, I can assume a water if necessary. And sorry, I meant to use black there. I got my benzene ring here. Still got a carbon with a double bond oxygen attached. I got a nitrogen with an ethyl and a methyl group over here. And then again, like I said, you got to add in some new atoms. That's why I needed the water to begin with. Right? I got a hydrogen onto that nitrogen over here that is now secondary. It can be named as an amine. Right? And I have this carboxylic acid, the benzoic acid. That's one thing I didn't necessarily do. Remember, this would be called, right? You can name this as a methylamine or as aminomethane, right? This one has to be named with a common name. You have to say ethylmethylamine, right? So we can still name those like we did before. Again, in this case, that would be bonus because it's a product you'd be naming. But otherwise, be able to break down your amides and just like you were able to form them. Now, this isn't actually a reversible reaction. If you guys remember from your notes before, technically, if I had this hydroxyl group and this amine, there would be an acid-base reaction. So I would never be able to get this to reverse to recreate my original amide, or at least not in current conditions. You can do reactions like that. You just have to have special enzymes that could be found in your cells, because you do that all the time in your cells when you're making proteins. So there's a reason why we're learning about amide bonds, because special bonds called peptide bonds in your proteins are amide bonds. So you can do it, but generally speaking, if you had a carboxylic acid and an amine, they would actually do an acid-base reaction. So there's a reason why I only have one direction for this arrow here, because only one way is allowed. I can't reverse this to make my amide again. I would need that acid chloride to make that work, right? So that's from before. Otherwise, the last two little things for amides, just because they kind of have weird names, these smallest amides are usually referred to with their common names. This one would be called a formamide. Because this is called a formic acid, right? And again, I already used this one a couple times, or at least I usually use this one when I'm naming. I use that acid prefix. This is an acetamide. Making a really funny D there. And again, acetic acid, that main ingredient in vinegar. Right, so these names are used pretty frequently. If I go backwards, maybe I could have called this a butyramide, because that's a common name, but I just typically don't use common names for things 3, 4, 5, more than 2 carbons. So it just depends on your preferences. But again, those two smallest ones are typically referred to as formamide and acetamide. So it's kind of nice to know that. All right, so that should be everything we need for now. I'll do some more derivatives